Welcome to the second video about neural networks. In this video we will see how we train a neural network. This video is part of a number of videos in which several aspects of neural networks are explained. Before you watch this video, please be sure that you saw the first video from the series, because there I explain how a neural network works, and specifically I use an example, a very small neural network, and in this video we will see how we train that small network. Okay. So what we saw in the last video was basically this network. So it's only one network, but it had like 4 different possible inputs. It was 0, 0, 0, 1, 1, 0 and 1, 1. And it gave as an output 0, 1, 1 or 0, which is basically the XOR function. So this is the network which in the last video I explained how it works, and in this video we will see how we have to train it. How can we train it? Because this is the trained network with all the weights, the correct values, but this network started its life differently, basically with random weights. Well, this is the view you see now is somewhere halfway the training process, but you see that it still has a long way to go, because this should be 0, this 1, 1 and this 0. And when I go back a little bit to the previous slide, then you see that really the weights still need to change until we get the trained network. So that's the subject of this video. How do we adapt the weights such that the correct output is generated? And we're gonna have a look at it again from in one situation. So I'm gonna explain the whole process with the inputs 0 and 1, but of course the same thing happens for the other inputs. Okay, so that's this network, and the basic key error, the basic key point is that we have to change the weight to reduce the error, but we have to find the most smart way to do it, the most efficient way. I will come back to that a little bit later. And the way to do that is with backpropagation. That's what most neural networks use to change their weight, to learn basically. Okay, let's shove it to the side. Basically the idea of backpropagation is that we start at the back. So when we executed the network, then it was input in and then it goes from the left to the right. But now when we want to change the weight, we will start at the back. And let's first see the last step of how a network works. So we had the nodes, the hidden nodes, those had values here, and they were multiplied by the weights, and basically they were inputs for this node, and it was all added together. And because this last node didn't have an activation function, this is basically already the end answer. And the key question now, and the error, because in this case we want it to be 1, the error is minus 0.38. So what's the key questions? Which change in weights is the most useful, is the most efficient? And this is really a key point, because you could say, well, we can change everything. But the thing is that each change in weight will have a disadvantage for another input condition. Yeah, let's say that the inputs are 0, 0, then it could be that that what we change here, that it will be worse for the 0, 0 condition. So we want to be really precise, really like a surgeon, and we only, when you have a body, we only want to make the part better which makes it sick, and leave the rest intact. So what we could do, we could see, well, we've got 3 weights which we can change, right? 1, 2, 3, and we could see which one of those is the most efficient if we change them. Let's say we change the first one, and because the node has a value of 0.42, then the addition of that is, or the delta of that is 0.42. If we change the second one, then we see that the added effect is really small. And that's logic, because this value is so low. This is really close to 0. So this weight doesn't really play a role. And what you will also see is that, of course, the last weight is the most efficient to change. Okay. So basically what we're trying to find is a rule that we with which we can calculate how much we need to change the weight and in which direction, but on the most efficient way, most precise way. Well, it turns out that a really useful rule for this is this one, and it shouldn't come as a totally surprise, because it's kind of in line what we saw here. So the weight which we want to change is equal to minus some kind of a learning rate, and I didn't talk about that yet, but it's how aggressively do you want to learn the network, and it can be too big, because it could be that you overstep your learning. So this is like a factor which you can put high or low, multiplied by the output of the hidden node times the error of the output. And it turns out that this is a really smart way to do that. Okay, let's apply this rule. So let's put it at the top, and let's apply this rule in this case. So we have the learning rate, and let's say, okay, then we have the output of the hidden nodes, we have the error output, and this combination should result in a delta weight. So a change in the weight. Let's calculate it for the first line, and let's say the learning rate is minus 1/4 times the hidden node times the output error. And so we should change it like this. And we can calculate this for all the 3 weights, all the 3 connections. Let's see what the impact is on the output of the output layer. So first we'll change the first weight. Let's get a little bit higher. Then the second one, well, that's probably not going to change. Yeah, a little bit. And the biggest change, which is also what we wanted, is in the bias neuron, in this case, the bias node. So it goes from 0.16 to 0.25. When we calculate now the effect of all those changes, we will see that the output will go from 0.6 to 0.72, which is quite a big change. So the error is really reduced already from 0.38 to 0.28, which is pretty cool. Okay. I talked a little bit about that changing a weight is good in one situation but bad in another situation, and I'll make it a little bit more visual for you. So what you could see that both in this situation, the weights probably have to change the same way, right? Because apparently it's pretty obvious that if this needs to get higher, then this one needs to be a higher value, and this one probably also needs to be higher. So that's beneficial in both cases. But if we look at one of the other input cases, 1, 1, then we see that this one actually needs to be a 0. So in that case, this probably is a bad idea to make it better. So if we apply that algorithm, which we just talked about, to this case, it will probably give a suggestion or recommendation to lower this weight. And also for this one. So what you see is that it's like a delicate dance or delicate balance. So all these 4 different input situations will give different recommendations. What you do in practice is that you all add them up together and take the average, and that's what you apply. But now you also see that it's so important to be really surgical, precise where you want to change the weight. Because each changing of the weight has a disadvantage for another situation. Okay. But what we did now is only train these weights, of those weights. We still have a lot more intelligence in the network. We could also train those weights, these weights. So what's a smart way to do that? Well, then we probably need to know which direction we want these nodes to go. So basically you want to know what's the error for those nodes. Because if we know the error for those nodes, then we also know how we should change the weights to get the error for those nodes smaller. So let's see how we would like the hidden nodes to change. Basically the top one in this case, and please remember we want the final output to be 1 in this case. The top one we would like to be higher because it has a positive weight connection to the output node. The bottom one from the hidden layer we want it to be lower as it is negatively connected. So okay. Can we again find some rule about how we would like those hidden layers to change? Well, we can see already that firstly it really depends on the output error. Do we want this thing to be higher or lower? So of course in the final formula this has to be in. But what we also see that it's important if this connection is strong, weak, negative, positive, etc. So we want also this connection. So those are the two aspects or elements which we want in a formula. But there's one thing still missing because differently from the output layer, in this case we also had an activation function. And what you can see already that if we have the input of a hidden layer node, if it's already in this side, so really positive to the side, we can change the weight, but it will not matter too much on the output of the node. So that's really not a precise change. It's going to be like a big change. It's going to be a change, but it hasn't a positive effect and probably will have a negative effect for another situation. And it's similarly to the when the input node is really negative. The input of the node is really negative. Input of the activation function. So what we ideally would like is that only in this area in between we really change the weight, and if the input is already here we don't care, if the inputs are already here we don't care. So how can we do that? Well, there's actually a neat trick. We can take the derivative of the activation function. That is this red graph, and this gives already the perfect shape because this one is 0 here and 0 here and it's higher here, so it really makes sure that we only make the change the biggest when it's the most effective. Okay, so then we have the third element, and with these 3 elements we basically can calculate the error of the nodes from the hidden layer. But that's pretty cool. Why? Because now, first let's apply it. Let's see the example. So we've got the derivative of the activation functions, we've got the weights of the hidden node to the output, and we've got the error. And what we see in this case is that we would like this neuron to be higher, a lot higher, and this one a little bit lower, but we don't care as much about this one as this one. So if we change weights here, we think changing the weights to this one is more important than this one because this value is higher than this value. But that's actually nice, right? Because this one wasn't really playing along anyway because it had a really pretty low value, so that's good. Okay, let's put them at their rightful place. Okay, but now we have a really nice thing because we basically know now how we want those nodes in the hidden layer to change. But this trick we knew already. If we know a node how it should change, then we know how to change the weights. But now we know how we want these nodes to change, so we can apply the same rule, which is pretty cool. This rule is basically the same rule as we had at the beginning. Although here it's for the hidden node, now it's for the input node. Here it's for the output of the error, now it's the error of the output, now it's for the error of the hidden node. So basically, yeah, I'm not going to explain this because we can just apply the same rule. Okay, this is pretty cool, but what if we have more layers, if we have got more hidden layers? Well, that's not a problem at all, because we can do the same trick again and again and again. It's like eat, sleep, rave, repeat, but then it's like calculate error, apply the rule, the delta error, change the weights, calculate the error, change the weights, etc, etc, etc. So this is a really simple solution. And what we see now, we also see the origin of the name of the algorithm, because what we basically are doing is backpropagating the error from right to left. And it works pretty cool. So that was the explanation of how to train a neural network. In the next videos we will show you some examples. Have fun!